Dear colleagues, we are going to start the second day of the conference, and the first speaker today is Pavel Velikhov. He is a principal engineer at Moscow Laboratory for Databases in Huawei, and he's going to tell us about the analytical database of Huawei entitled GaussDB. So, Pavel, the floor is yours.
Thank you. Yes, so I'm working in Huawei right now in the Moscow Database Intelligence and Optimization Technology Center. And we're focused on building GaussDB-A, which is our analytical database. And Huawei is not really known for building databases so far, but the story started about 8 years ago. Huawei started building its own database system based on PostgreSQL. And over the 8 years, the technology has matured, so a lot of the code was rewritten. We've added a vectorized execution engine, a column store, rewrote a lot of the code. And about a year ago, this product became a real product of Huawei. So started selling this to external customers. Before it was used internally in Huawei's projects. And also recently, all of the databases moved to the cloud business unit. So that they are now available in Huawei Cloud. In Russia, for example, we're providing equipment and software for SberCloud, so it's possible to get it in Russia as well. And we have big customers in China, so top banks and telecom companies, and slowly getting some traction with customers all over the world. So I'm gonna talk about GaussDB a little bit and introduce the Moscow Database Intelligence and Optimization Center and the projects we're doing with GaussDB. Okay. So GaussDB is a MPP, massively parallel processing database system with shared nothing architecture. It's in the class of databases like Teradata or Greenplum or Parallel DB2. So we deploy on clusters sometimes of 200 machines. So also the networking layer has been reworked. We have a large scale cluster communication network. And we are using hybrid storage, row and column hybrid storage. And I'll talk a little bit about this later. So you can store your data in rows, but also for high performance analytical queries, it benefits to store data in columns. And we are, of course, we're compatible with Postgres 9.2, so we offer standard SQL for analytics. And we also have tools to support migration from Oracle and Teradata. And also, GaussDB is a first-class player in big data landscape. So we allow, you can query Hadoop files, so org files on Hadoop through our foreign wrapper extension. And since we moved to the cloud services, we're working on a lot of cloud features, so like automatic resource scaling and multi-tenancy and all sorts of new things for us that the cloud mandates. In our architecture, we use multiple coordinator nodes. Coordinator nodes are like the master nodes in other systems. and they're responsible for receiving the query, optimizing the plan, and creating the global plan and sending it around the cluster. So it's a fail-safe system. So if one coordinator fails, then the application can access another coordinator. So we achieve high availability with this. Some of the services are single instance. So for example, Global Transaction Manager that provides transaction timestamps. It's a single instance for the whole cluster, but the coordinator nodes are replicated. And usually we set up multiple data nodes on the same machine. For each local disk, there's a data node, and then we have for each machine, there's a series of data nodes that are servicing that machine. So when the query arrives to the coordinator node, we run it through an optimizer. So we use the regular Postgres optimizer that has been tweaked a little bit to support, to consider data distribution and shipping of query results around, and our vector engine, of course. So the cost model for the column store is included there as well. And so then the query plan is generated by the coordinator. It's shipped to the data nodes, and they ideally they would process all the data locally, but sometimes shipping is required. So data nodes communicate to each other and ship to other data nodes the data that is required for distributed joins or aggregations. So then the data nodes return the result to the coordinator node, which completes the aggregations or the operations, and the coordinator returns the result to the application finally. So we're using a lot of tricks to maximize processing performance and resource utilization. So of course, it's a distributed MPP execution framework, and we support up to 1,000 servers now. So, and tens of thousands of CPU cores in our database. We also make use of SMP parallel processors as much as possible. So compared to Greenplum, for example, GaussDB is a multi-threaded system. So each thread is responsible for its own part of the plan and its own partition of the data. We make use of SIMD a lot. So for in our vector engine, you make use of SIMD as much as possible, and we have we package batches of column data together and send them through SIMD instructions. And we also use LLVM just-in-time compilation. So we generate machine code from some parts of the queries. And we're trying to expand this to whole plans. Actually, right now we have a research project with the Institute of Systems Programming that is trying to compile the entire query into LLVM. So we have both row and column store, and there are some benefits of, so for point queries and data updates, the row storage is much more efficient than the column store. So it can be used for some basic transaction processing. We're not an OLTP system, we're focused on OLAP, but you can do basic transactions on the row storage. And then for statistical analysis or for fast loading, the column store shines. It's much more efficient for OLAP queries. So currently we're trying to get our customers to use column store as much as possible. If they still have some data in the row engine, it gets converted. So the plan starts as a column store plan with the vector engine, and then if we see a table from a row engine, then we shift to the row executor and continue with the row executor. And we have our ideal scenario is when the customer is bulk loading data in batches, and we have a parallel loader that achieves very high performance, so terabytes per hour, so maybe hundreds of terabytes can be imported in parallel per day. And this is important because some of the customers we have, they are now past the petabyte threshold of using GaussDB. We continue to work on this technology and make it even better. Now, the Moscow Database Intelligence and Optimization Center has been set up in last year, so in September of last year. We currently have 3 groups. So one group is focusing on MySQL on the cloud. Our team is focused on GaussDB. We have one more small team that is doing all sorts of database-related projects. So the GaussDB team is about 10 people now, and the goal of the group is to do top-level R&D and then implement the results in GaussDB product. And we're focused on mostly performance optimization right now. So one of the projects we're working on is better query optimization with machine learning, and it's known that modern query optimizers are still using very basic statistics in their cost functions. And as a result, they make really wildly erroneous estimates of cardinalities. And then from cardinalities, they compute the costs and they get the costs completely wrong. So there was a great paper on VLDB, how good are query optimizers really? And it was shown that commercial query optimizers predict cardinality estimates of join results around 4 or 5 orders of magnitude incorrectly. Usually they underestimate the size of the joins. After we have about 6 joins in the plan, and it's common in all app queries, it's common to have tens of joins or more. So it's a really serious problem. And we're currently focused on join order optimization, so selecting the correct join order, and we're doing it with deep learning. So it has been shown in the research literature that deep learning is, it's possible to use deep learning to avoid these problems. And what is happening is that the neural network that replaces the cost function is trained on real distribution of data. So it's trained specifically on a concrete database instance, and it can learn all sorts of correlations and distributions of data, and it can predict cardinality estimates and costs much better than basic statistical features used in optimizers. So we're working on an intelligent optimizer project to build this into a commercial system. So there are, of course, a lot of extra challenges. We have to have a, we cannot just stop the whole system and have the optimizer train. So we have to do it concurrently with the workload. We have to sample the workload and find out what the real execution times of the queries were and what the different subplans that the optimizer considered were, and learn from that. So very exciting project. Another project we're working with is combating data skew. So in shared nothing MPP systems, data skew can really compromise performance significantly. What's happening is that when data is distributed, either when we're loading the data or when we're doing query processing, some nodes can get a lot more data than other nodes. So for example, you could have one node get 90% of the whole data in the cluster because the distribution key was skewed. And this slows down query processing significantly. Everybody's waiting for the last node to finish. And most databases actually do suffer from data skew because power law distributions are very common in practice. Usually databases were evaluated on artificial benchmarks like TPC, but now we're looking at real data like IMDb data and other data sets that exhibit these properties. And we're building skew resilient algorithms and techniques for GaussDB that automatically mitigate these problems. And another project that we're starting now is so in-memory processing. So in-memory database technology is really taking off recently, both for OLTP and OLAP systems. And a lot of customers further demand hybrid transactional analytical processing capability from the database, HTAP. And in our view, it's easier to achieve HTAP with an in-memory database. So we're researching how to add this capability to GaussDB to have a in-memory HTAP storage and engine. And some work has been done already for GaussDB. So there was a paper, I believe, on Sigma, the industrial scale OLTP using main memory in many cores. So it's, and it has been already integrated into open source GaussDB. But the focus has been on OLTP. And now we're looking at more of the OLAP with some OLTP support. These are the three projects we currently, so three big projects we're currently working on. We're also soliciting collaboration projects from Russian universities and institutes in Russia and abroad. And so typically we engage in one-year collaboration projects, and the topics are usually close to the core of GaussDB. But they can be fundamental research topics as well, so in the area of databases. We're currently collaborating, so we are collaborating with the Institute of Systems Programming right now, and they're building a full query LLVM system for us. And we're starting up a few projects this year with the Russian universities. So this is it. I was planning to have some questions and answers session. So please go ahead and ask some questions, and let's have a discussion.
Okay, Pavel, thanks a lot. So we have quite a lot of time for questions and discussion. So would anybody would like to ask a question?
May I ask a question?
Yeah, sure. Yeah, sure.
In the past, we have had in databases a lot of optimization facilities for having joins computed in a proper way. Is it inheritable for all this kind of storages you are using?
So sorry, I kind of missed.
We have had in the, let's say, 80s and 90s a lot of research how to perform joins, how to perform different operations in relational databases. And since the column store is nothing else as a 6 normal form, I might think that you have to inherit all what has been done in the past. For instance, the order of joins, which joins are pre-computed, pre-fetched, and anything else. Did you consider those things?
No, so we're using, we started with a Postgres dynamic programming basic algorithm, and we just extended the cost model of the optimizer. So it's still pretty, so while of course there's a lot of code and there's a lot of special cases to handle outer joints, semi joints, everything else, but the whole system is very similar to like system R optimizers. So
Mm-hmm. I think it would be worth to compare it somehow with the old stuff.
yeah, that's very interesting.
Mimo was the first column store we have had in the 70s. They have also a lot of problems like similar to those you have been declaring now.
Mm-hmm.
Now this Mimo is called Rapid.
Okay.
Okay, dear colleagues, more questions? Okay, in this case, I do have a question. Okay, I wonder concerning the application of deep learning for the optimization of queries. So could you please, Pavel, could you please comment a bit the techniques you are going to apply? So I wonder first, do you consider pre-learning some general neural network for the general case, and then some specific additional learning for some concrete database? Is it true, or something else is applied?
No, we actually start learning the neural network from scratch on every new database instance. So we have a database instance. Queries are starting to come.
Okay.
We observe the queries. What we do right now is we let the optimizer, the current optimizer, optimize the queries, and we look at all the suboptimal plans that the optimizer has so far considered, and we look at the cost estimates that the optimizer has generated for those subplans. And so, for example, a big query like with 18 joints can generate about maybe 800,000 examples with a subplan and its associated cost. And we learn on this. So we try to mimic the current optimizer, and we learn to make compatible predictions with the existing optimizer. And then as we get real execution data, we fine-tune the optimizer to predict the actual running time of the queries. And it's all happening while the query stream is running.
Okay, thanks. But according to your experience, how much time does it take, or how much queries does it take to learn the network to achieve some reasonable accuracy, or something, or some more metrics?
So right now we're experimenting on IMDb dataset and IMDb query set. So it's about 100 queries. And that is sufficient to learn the model. So 100 queries is now sufficient. So even less, so maybe like 50, 80 queries are enough.
So, and what is the accuracy for the estimations?
Well, so we're close to real running time. Maybe our errors maybe 2 or 3 times within the actual prediction, the actual running time of the queries. So we're pretty close to the real results. Now it turns out that it doesn't really matter. You don't have to build a perfect predictor of running times. You just need to get the hard cases correctly.
Okay.
The hard cases with many joins. So we're focusing on them right now.
Okay, thank you. So do we have more questions, please, colleagues? Okay, I have additional questions. So you mentioned that a SIGMOD paper in the industrial paper was published concerning the application GaussDB as OLTP database.
Mm-hmm.
Am I right? And but within this presentation, you are mostly talking about the GaussDB as OLAP solution.
Yes.
But
yes.
And you know, it seems a bit strange that when you're considering the same database, both as a specific and very powerful OLAP solution, and also as a very powerful OLTP solution. Could you please comment how is it possible? Maybe that's different modes of operation or something else, or
no, so there was a research project. It was not done by the Moscow group. It was done by Israeli Research Center in Israel, in Tel Aviv, and there were they specifically decided to build an OLTP engine inside GaussDB, so to make the next step towards HTAP architecture. So we don't completely agree with their approach. So we're thinking about building an in-memory column store, which is more geared towards analytics than a roast engine. But I think we're moving in this direction. So we're moving in the HTAP direction, where you don't separate OLTP from OLAP as much as we used to. So a lot of customers are saying that they don't want to create complex ETL pipelines from their OLTP database to the OLAP database and maintain that whole setup. They want one database where they can do some transactions, so maybe not a very high loaded transactions, but massive amounts of data, and they want to do analytics on it. So we're starting to move towards HTAP architecture.
Okay, thanks a lot. So we'll have a couple of minutes for additional questions. Do we have more questions? Okay, I do not see any hands raised. So Pavel, thanks a lot for quite interesting talk and for answering questions and discussions. And as all of us can see, Pavel also proposed some ways for collaboration with the industry and Huawei exactly. So this quite a way to collaborate of academy with the industry. So Pavel, thanks a lot for quite interesting invited talk. So our first session is over. So and the next session will be in 10 minutes. Okay, thank you.